Thank you so much to the organizers, including our paper on the program. So it has been another great conference. This is joint work with Charlie Columbus and Harry Mamai-Sky. And we have been working on this project for some time, but didn't have a lot of chance to present it. And indeed, this version, this will be my first time presenting this latest version of this project. So news and how it is associated with changes in stock market returns and risk is a key question in asset pricing and the subject of research for many years. And recently, economists have brought new tools, including various aspects of words that appear in news articles or other textual sources. And as you might already know, actually, this is a very fast growing field. So motivated, by their ability to predict returns and risk in the stock markets and their availability in real time on a daily basis. In this paper, we examine the predictability of oil market outcomes using textual measures. I mean, why focus on the oil market? So I think several reasons. I mean, oil market receives more attention among economists or like news outlets for many reasons, from its significance for producer and importer countries, as well as being a key variable in generating macroeconomic projections and macroeconomic risks. So what do we do? What do we do in this paper? So we construct a parsimonious mapping of news flows using techniques that have proven, valuable elsewhere, and explore their usefulness along with a broad range of macro and financial variables, as well as measures capturing market risk premia for predicting oil futures and spot returns, energy company stock returns. We are considering 3 oil majors: change in realized oil volatility, change in oil production, and change in oil inventories, both in sample and out of sample. So in terms of our approaches and findings, our period for the analysis is from April 1998 to March 2020, which is constrained by the availability of the Thomson Reuters data. Our news outlet is Thomson Reuters, which is actually an ideal news outlet, as it's based in many countries. It's in English, and it's kind of like sophisticated outlet for market participants. So what we do, we actually consider weekly observations, and our forecast horizon is 8 weeks, but our results are qualitatively similar for 4-week ahead results as well. So we start with a large set of predictors, more than 30 predictors, and we aim to be explicit and systematic about which variables to include in the empirical analysis. So in doing so, we consider a forward selection approach, given its simplicity, and also we think that this process mirrors what researchers likely implicitly do. Even after controlling for selection bias and overlapping observations, we find compelling evidence of in-sample predictability. So both our new text measures as well as traditional non-text measures are important in predicting, these oil market outcomes. And when we kind of examine how to interpret these measures, could they be actually capturing some, some omitted risk factor? We actually find that they don't really look like as proxies for some omitted risk factor. So, we got quite excited seeing this, high in-sample, impressive in-sample predictability. And then the next question we ask is, does it translate into out-of-sample performance? And our answer is no. So we consider 3 approaches for out-of-sample predictability. The first actually consider the selected in-sample regressors as given. The second approach allow for time variation in predictors. And our benchmark model is the rolling mean of the dependent variable. And overall, we find that actually both of these approaches, show poor out of sample performance. So this, lack of success brought us to our third approach. In our third approach, we are engaging in a brute force search over all possible two-variable forecasting models for successful out-of-sample forecasting. So indeed, the title of our paper is describing, our conscious, transparent, and systematic data mining, as we are trying to figure out how one systematically can do this kind of forecasting research. If one do this, actually, we find that there's evidence of out-of-sample predictability. Unfortunately, we couldn't identify a systematic method for finding successful forecasting pairs ex ante. For the sake of time, I will be very brief in terms of the literature review. This is, related to this, finance literature, where they look at actually these forecasting variables and their performance in sample in predicting returns on, commodities or other asset markets. There's also, new studies looking at the usefulness of NLP measures in the oil market. For instance, last year, DIPA presented their paper on this. And then we are aware of this, big literature, on these, forecasting energy prices, oil prices. But I mean, our approach, the approaches used in these, studies, the frequency, the time frame, etc., are a little different from, what we're trying to do. So let me continue with the data and construction of our variables. So our raw data sources are coming from these sources. As I said, our time frame is 1998-2020, and we consider weekly observation mainly because our inventory, and production data is coming from the U.S. and the U.S. data is weekly. Although we have, the prices as well as, news data is available daily. We are constrained with this, production inventory data. I already mentioned about the dependent variables and our oil majors. For oil majors, we consider BP, Exxon, and Shell stock returns. So what are the set of our predictors? We consider the lag-dependent variables, and then we consider, the macro or financial variables used in the, literature for predicting returns on commodity returns. So these variables are listed on the slide. We also add several measures of risk premium. So we consider the volatility and risk premium for stock markets and as well as the oil markets. But we also, constructed three estimates for stochastic discount factor using a rolling window, a growing window, and also constructing an SDF using a full sample. So the first two we are using in the out of sample, and the last one we are considering in the in-sample analysis. So in terms of timing of the variables, we make sure that actually our predictors do not overlap with the variables that they are predicting, and also to maintain the consistency of the predictors, we obtain them over the last 4 weeks. So let me move on to introducing our new variables. So our corpus is, as I said, Thomson Reuters, including more than 2 million articles, which is about 10% of the TR articles. So our measures are article count, frequency of topic, sentiment of topic, and entropy. I'm going to be very brief again for the sake of time. I'm not going to go into any details. So article count is, when more articles are published, is it meaningful, or whether more articles are written on a certain topic, it's meaningful, which is the frequency of a topic, and then the sentiment of a topic. And entropy is capturing kind of the unusualness, which is a measure of an unusualness. We also construct and we averaged like these text measures over the previous 4 weeks. So we also consider 3 measures of aggregate news flows, which are the principal component, which are based on the principal component analysis of these, frequency measures. We have 7 topics. I'm going to come to that. So 7 frequency measures, then principal component of these 7 sentiment measures, and then we combine all these 14 frequency and sentiment measures and obtain these principal components and have these aggregate news flows. So how do we identify these topics? So in the literature, there are two kind of main ways to extract like topics. One is Louvain and the other one is LDA. So here we focus on Louvain algorithm, but we also looked at LDA, and which give actually similar topics. So the analysis, this, as I said, the 7 topics are identified by applying the Louvain method to a list of energyverse, and this energyverse, actually we constructed an initial set of energyverse ourselves using several sources, and then we use this algorithm to come up with another list, and then we constructed these topics. So let me actually continue with the word clouds to help you understand how we come up with these labels for each of these topics. So these word clouds are coming from this analysis, and 7 is also again determined by the data. So looking at these, so the larger font shows the the greater occurrence of the work in the corpus. Just actually looking at the words in each word cloud, we are independently and instantly label these clouds. So like we label them as company, global oil market, environment, energy, power generation, crude oil, physical, refining and petrochemicals, and exploration and production. And we actually, like looking at some of the sample articles, their titles, their sentiment frequency, we were also able to actually validate that actually they make a lot of sense. Just to quickly also looking at the, like topical frequency over time, as well as, like for instance, the topical sentiment over time. What I would like you to take away from this one is that, there's a lot of time variation in these measures. In other words, they are not really capturing the same thing, which is a good thing, especially if you are thinking in terms of like doing this type of research. So now let me continue introducing our variables. Let me continue with our empirical analysis. So again, I mean, we have, for instance, like about 19 textual measures. We also have these, macro or financial variables. So we have a broad list of variables that we would like to use, like to actually to predict 8-week ahead returns and changes. We have 8 dependent variables. So how do we do that? We actually employ a forward selection model and choose 7 predictors successively with the greatest contribution to the model R squared. So given that the model is, estimated using weekly observation with, either 4-week or 8-week ahead overlapping observations, and also that we are using, we are employing a forward selection method. So I mean, it is likely that like the R squares, there will be upward bias to R squares and downward bias for standard errors. So as a result, we actually try to adjust for the selection bias and overlapping observations by constructing bootstrap distributions for R-square and R-squares and T statistics. So this figure is just little figure is just to give you an idea about what we are trying to do. So this is actually the bootstrapped distribution for the adjusted R-square under the null of no predictability, and so here we actually present the empirical adjusted R-square. So what it tells us is that actually like more than 99% of the simulated adjusted R-squares are actually less than the empirical R-square, and we actually take this into consideration while we are actually thinking about our in-sample results. And we present in this table our bootstrap p-values. So in terms of our p-values, a p-value less than or equal to 0.05 means significance at the 10% significance at the 10% level. Okay, so here this table presents our regression results for 8 dependent variables, and here we only included the predictors which are selected by at least one time. And the coefficient presented are standardized coefficients, and the blue ones indicate the non-text variables, selected non-text variables, and the red ones indicate the selected text variables, and the bold ones show significance. So first looking, and at the end we also report R-squares, mean, and the CDF, which is the percent of simulations with an adjusted R-square less than the estimated R-square. So overall, if you takeaways from this in-sample analysis are as follows. So I mean, looking at the the coefficients, they range from like 0.09 to like 0.37 in absolute value, and among the selected predictors, about 2/3 of the selected variables are significant. The R-squares are also looking good, and looking at the CDFs, they suggested actually these empirical R-squares are highly unlikely to have been generated by chance. So looking at then the distribution, like the blue versus like red colors, as you can see, overall the text variables are selected as much as the traditional non-text measures, and several of these selected measures are chosen to be statistically significant at least 2 times. So for example, when we look at, for example, the sentiment of sentiment of exploration and production related articles, for instance, BP returns, change in inventories or change in production, they are all forecastable with the sentiment of exploration and production related articles. So overall, this suggests that actually both text measures and the traditional non-text measures are important in forecasting energy variables, but overall, of course, for some dependent variables, text measures are more important than the non-text measures, for example, as in the case of the change in spot prices. Of course, I mean, one thing that we considered was that especially looking at, for instance, the future returns, this seems to be more actually forecastable by non-text measures. What can be wondered, what are these text measures are actually kind of capturing? Could that be could these selected text measures, could text measures be selected because they are proxies for risk? So to be able to actually, I'm not presenting results in here, but to be able to kind of simply address this question, we take these forward selection models, considered, and then we add our risk premium measures one by one. to these 7 variables selected in the stepwise forward selection. And then we look at the coefficient estimates, whether, for instance, the coefficients on the text measures are actually, does reduce to, to 0 when we add these text measures. And actually, they don't. So adding these, risk measure does not reduce the coefficients on the text measures towards 0. So we interpret this as actually they probably not capturing, risk, or may not be, considered as proxies for capturing some omitted risk factor. So overall, we find really impressive in sample predictability, after careful controlling for selection bias, as well as overlapping observations. So as I said in the beginning, the next question is whether this translates into out of sample performance. In doing so, what we are doing is the first approach, as I said before, is actually evaluating the effectiveness of our in-sample model selection technique for out-of-sample forecasting. So what we are doing is we are just taking these, 7, selected variables from this model over the entire sample, and then we run rolling 5-year loss regressions to estimate rolling coefficients for out-of-sample forecasting of 8-week ahead changes or returns. To control for the possibility of overfitting a 7, a 7 independent variable model in 5-year training windows, we also consider a 2 variable version of the forward selected model, and did the whole process similarly for this 2 variable version as well. So our, what we are considering is as our benchmark model is the, rolling 5-year averages of the dependent variable is what we call as the constant model. So this is our benchmark model. So we are comparing the MSE of these, MSE of these 2 or 7 variable loss models compared to the MSEs of these, constant models. And here in this table, we actually present the MSE ratios relative to the constant models. As you can see, actually, we don't actually see good performance only.
Nida?
Yes.
Sorry, we have 5 minutes.
5 minutes? Oh, okay. Poor performance. So let me move to the second approach that we considered. In the prior approach, we have, our variables are fixed over the sample. So, but however, it is very likely that, the usefulness of these, forecasting variables may change over time. So to take this into consideration, what we are doing is that we are running univariate regressions of each forecasting variable in rolling 5-year training windows, and then we rank them according to their standalone R-squareds. And we classify them as text and baseline, and then picking these given ranked baseline and text variables, then we are considering 3 different type of forecasting models. One consider the let me actually go to this one. So one considers one top text variable, the other one is considering one baseline variable, and also we consider one-on-one. So let me actually present these results. So here the left column presents actually the performance of these models, again relative to the constant model. So as you can see, I mean, just like neither, like 0-1 or one-on-one text models are really overall doing a good job. And we also consider to be able to allow for the possibility that maybe more than one variable is actually useful. So we consider a 2-variable version as well, considering 2-top, text 2-top and 2-2 combination. And the results are not still, like good. And then finally, we are also exploring whether adding text measures actually like make the model, like perform compared to including only baseline variables, kind of examining the incremental value of text measures. And this two right, these based on this column shows the results. And actually, overall, the results are more positive. It's suggesting that actually adding text-based information to traditional predictors is useful, however, not useful, sufficiently useful to outperform the constant model. So as a result, we, then this led us to, our, a final exercise where we actually consider a brute force data mining exercise to find successful, out of sample, predictability. So what we are doing is that for every dependent variable, we are checking all possible combinations of 2 forecasting variables. So we have 39 forecasting variables. So there are 741 something, potential combinations. So for each of these models, actually, we are trying to find out the successful combinations. Successful means they are actually outperforming the constant model. And this is actually what we get. And again, we are running similarly loss of regressions. So for instance, future returns, we find that actually out of the 700 something, potential models, 17 of them are successful. That's 17 pairs, forecasting models, which includes pairs of variables are successful. We find it is 206. And overall, the means actually of these MSE ratios change between 0.9 and 0.99. So when we look at, for instance, which variables are selected in this successful models, so there are more than 1,000 selected variables. So the top is showing these text measures, and the bottom shows actually the baseline variables. We see that actually 400 something variables, the selected variables are text, and more than 60, close to 677 are actually their non-text measures. So, I mean, and of course, there are a lot of variation in terms of how often they appear in these successful models, but, the risk premium measures seem to be actually, appear quite often. And there are also a few of these, for instance, SEP and others that appear, in these successful models. I mean, overall, out of 5,900, potential models, we find 540, of them, outperforming the constant model. So, I mean, overall, the takeaway is that, yes, I mean, with such conscious and, transparent, data mining, we are able to find, successful out of sample. However, we couldn't really identify any systematic algorithm for finding such successful forecasting pairs X ante. And so overall, just to wrap up quickly, so in this paper, we construct new measures using methods that are proven useful elsewhere, and we combine these measures with some more traditional, forecasting variables. We find strong in-sample predictability even after controlling for selection bias and overlapping observations. Overall, NLP measures are useful in predicting, oil market outcomes. But it's difficult. We find it difficult to identify a systematic strategy leading to out-of-sample performance better than the rolling mean of the dependent dependent variable. But when we data mine, again, consciously and transparently, then we identify many successful out-of-sample forecasting models, including our new NLP measures. So two open questions remain. So first, does such algorithm exist? And will any of our identified successful out-of-sample models continue to outperform in the future? This is something that we want to actually explore in the next few years. So that's all I have. Thank you.